Hello, today's lesson is going to be 1.2b. We're going to be talking about real numbers again. This is the second part of a two-part lesson, and we're going to be applying real numbers to real-world situations. So let's get started. Share my screen with you. And hopefully, there we go. Hopefully you're having a good day. It's running a little bit slow. We'll see how this goes as far as slowness. Today we're going to be identifying real numbers in real world situations, and we were going to be able to, at the end of this lesson, I can identify sets of real numbers in real world situations. And again, we're still working from NS1 standard. So let's move on. So here's my math meme today. See if you understand this one by now from last lesson. You should. The imaginary number I is saying be rational. I'm going to minimize myself here so you can see it there. And pi is saying get real. So do you get it? So, okay. Hopefully you get that joke at this time. Okay, a little bit of review. We have our chart from yesterday. And here's a review question. Write all the names that apply to this number, negative 1.5 repeating 5. Pause the video and see if you can write down all the names that apply to this number. Then come on back. Okay, so let's ask our questions. Is it a whole number? Is negative 1.5 repeating a whole number? So that answer should be no, because why? Because whole numbers are the counting numbers, 1, 2, 3, 4, 5, and 1.5 is not a whole number. How about the next one? Is it an integer? Integers are the negative and positive counting numbers. So again, because it is a 1.5, it's not an exact negative 1, negative 2, negative 3. It is not an integer. Next one. Is it a rational number? Can you write negative 1.5 repeating as a fraction? If you can, it is a rational number. How could we write it as a fraction? Well, we could, right? 1, and remember our shortcut? 5 repeating. It's going to be 1 and 5/9, right? And then the negative sign. So negative 1 and 5/9. So yes, it is a rational number. Next question. Is it an irrational number? So if it's rational, it cannot be irrational. So no, it is not an irrational number. And the last question, is it a real number? Well, all rational numbers are real numbers. So yes, it is a real number. So did we cross off the ones that it was not? I thought we did. I must have cleared my lines by mistake there. So there, we've got it. It's a rational and a real number. So let's bring down our box. Negative 1.5555 repeating is rational and real. Yay. Okay, let's move on. Another review question. Decide if the statement is true or false. No integers are whole numbers. No integers are whole numbers. Is that true or is it false? Well, we know that integers can be negatives and positives, and whole numbers are positive integers. So that is false. Every whole number is also an integer, so the positive integers are whole numbers. Number 2, true or false? Are all negative numbers are integers? Are all negative numbers integers? That should be false. Why? Because negative numbers can be integers, but all of the in-between negative numbers, such as negative 3.5, negative 20.42, negative 2.5, they're not integers, are they? but they're still negative numbers. So try to think of examples to figure out if a statement is true or false. Okay, it's your turn to try a couple review questions, and we'll see you back in a moment. Okay, hopefully you did well on those review questions and you're understanding real numbers really well. Okay, we're going to classify some real world numbers. Write all the names for numbers that apply to this real world situation. So a baseball pitcher has pitched 12 2/3 innings. So we're looking at the number 12 2/3 here, and we're going to ask ourselves, what does that classify as? So we ask ourselves, is it a whole number? No. Is it an integer? No. Is it a rational number? Yes. Is it an irrational number? No. Is it a real number? Yes. So it is rational and it is real. So 12 2/3 is rational and real. Okay, let's go to another one. Okay, the length of the side of a square that has an area of 10 square yards. Now this one might be a little more difficult. I'm actually going to put a little white box here so that we can cover up some of the previous one for a minute so we have a little bit of writing space. Okay, the length of the side of a square that has an area of 10 square yards. So let's draw our square. Oops, there's a square. And what is the formula for area? The formula for the area of a square is length, L, times width, W, right? We know that the area of a square is 10. I'm going to put that in the middle because that means that's the area. It's 10 square yards. So YD with a little 2 by it. That means square yards. If I can fit the little 2 in there. Now, the length of the side, we don't know. So we're going to call that X. And we know that because it's a square, both sides are going to be the same length. Okay, because the square has all equal sides. So now we can fill in what we know. We know that the area is 10, and we know that length is X, and width, the dot for times, width is also X. So X times X is really X squared. And this is something that you would have probably encountered last year. Not sure if we were able to get to exponents a whole lot. So 10 is equal to X squared. And then to solve this, if you go back all the way to lesson 1.1a, you have to find the value of X. You have to square root X squared, but you have to do the same thing to both sides, right? So then we know that the square root of X squared is just, I'm going to go over here now. The square root of X squared is just X. And then we're left with the square root of 10, right? So we know that X, or the side length, X, is square root of 10. So we know that the sides of this square are both square root of 10. Now, we have to decide and classify the square root of 10 because we now know the length of the side. So what is square root of 10? Is square root of 10 an integer? No, it is not. It is not a whole number. It is not a positive counting number. That's whole number. So it's not a whole number. It's also not an integer because it's not a negative counting number either. Is it a rational number? Is there a number I can multiply by itself to give me an answer of 10? No, right? It's like one of those imperfect or non-perfect squares, right? So it's like our square root of 8 from our last lesson. There is no number I can multiply together to give me 10 as an answer that's perfectly going to give me 10. So therefore, it belongs in the irrational column. And irrational numbers are also real numbers. So it is both irrational and real. So I'm going to clear my drawings. And there, I believe it should come down. If I did it right, there it is. Irrational and real. So that's how we classify that one. Okay, let's move on a little bit. Do some more problems. Identify the set of numbers. Okay, this is a little different. I'm going to go back one slide and look at the directions. So if we look at our directions from this slide, it says, write all the names for the numbers that apply to these real world situations. So basically, we're wanting to know all the names, okay, of the numbers. So we picked rational and real for the first one and irrational and real for the second. But we wanted to know all the names. Now the next slide here, go back to that now, isn't asking us for all of the number classifications. It's asking us for the best one. So identify the set of numbers that best describes each situation and explain your answer. So let's do an example. The number of people wearing glasses in a room. What's going to be the best description? Whole number, integer, rational number, irrational number, or real number? What's going to be the best descriptor? Well, let's start with integer. The number of people wearing glasses in a room. It could be an integer, but remember that integers include the negative numbers. Have you ever heard of a negative person before? I don't mean in the terms of an attitude. I mean like negative in terms of quantity, right? There's no such thing as a negative quantity of people, right? So it can't be an integer. That's not the best way to describe it. How about a whole number? Would people be 1, 2, 3, 4, 5? Exactly, they would be. So whole will work. Is that the best descriptor? Let's see. What about rational? Rational includes numbers that are negative but also positive. It includes like 1.5, 2.5, etc., right? So could you have 2.5 people wearing glasses? Or 1.5 people, or 1.5 people wearing glasses? No, you could only have a whole person unless you saw them in half. You pretty much have to keep them whole, right? So the best answer would be a whole number. So whole numbers is the best way to describe people wearing glasses because people can only be positive counting numbers. You can't have half a person, right? And they can't be negative as well. Okay, let's try another one. The circumference of a flying disc having a diameter of 8, 9, 10, 11, or 14 inches. What would be the best number category to describe the circumference of this disc? Remember, circumference is the distance all the way around the circle, or all the way around our disc, the measurement of that. So, and it's telling us our diameter, that's our from edge to edge, right through the center. That's our diameter. And they're giving you a choice of 8, 9, 10, 11, or 14-inch diameters. So what would be the best number to explain that? Remember the the circumference formula for a circle? Circumference is equal to pi 2r or pi d, pi diameter. So pi times the diameter of 8, 9, 10, 11, or 14 would give you the circumference of this flying disc. Well, what do we know about multiplying any number times pi? Pi is irrational, right? Pi never ends. Pi could go on and on and on. So there is not an exact number for pi. So if I multiply a non-exact number, an irrational number, times a positive number such as diameter, I can only get out of that an irrational number, right? If I multiply pi times anything, I'm not getting a precise answer. I'm getting something that's a close estimate. So that because of pi in our formula, that makes this number the best choice to be irrational. So let's clear and let's bring that down. Irrational numbers would best describe the situation because circumference calculations require multiplying the diameter by pi, which is irrational. Okay, let's try another one. The amount of water in a glass as it evaporates. What is the best category of numbers to describe the amount of water in a glass as it evaporates? Could it be evaporating at, like, say 5 ounces and then 4 ounces and then 3 ounces and then 2 ounces and then 1 ounce and then 0 ounces? Yeah, I could do that. But think about it. Is a little glass full of water here going to evaporate? Say here, it's starting here, and this is 4 ounces. Is it going to evaporate exactly 1 whole ounce? The next time you read it, maybe, but it's continually doing it, isn't it? So it could be the next time, it could be 3.96 ounces, right? And the next time, it could be 3.92 ounces. We don't know, but we could say, so basically, it could be any one of those numbers in between on the number line. So if we had our number line here, and we had 4 and 3, here's 4, here's 3, let's put another one, here's 2, here's 1, and then here's 0 when none of it is left. We could have it evaporating somewhere between, get a different color here, somewhere between here and here. So like that's where 3.96 is going to fall, and that's where 3.92 is going to fall. We could also have it evaporating between 2 and 3, and between 1 and 2, and then between 1 and 0. So it could be any number between those numbers, right? So it could maybe be a whole number, but it might also be what? It could also be an in-between number. It could be a rational number. So let's put that in there. It's a real number as well because the amount can be any number greater than 0 and can be a decimal or fractional amount. It could also be an irrational number. The reason why real numbers is the best choice is because it could be some small percentage of, like, let's say square root of 8, right? It could be something like that as well. It could be some very, very small decimal amount. So real numbers is the best. Okay, let's go on. Next one. The number of seconds remaining when a song is playing displayed as a negative number. So as the song is playing, the number is going to go down, right? Negative, displaying as a negative number. So can seconds be in between numbers? Let's take a look. Real numbers are best for this as well. The number of seconds left can be any number, fractional, decimal, or whole less than 0, right? Any one of those could be possibility. So real numbers describes it. Even an irrational number maybe, but not quite. Okay? Now it's your turn to have a couple statements and describe either how to classify the number in all the different categories or how to pick the best number to classify a statement. I'll see you back in a minute. Okay, we're going to talk a little bit about higher order thinking. What type of number best describes 0.9 repeating? Same thing, kind of what we were doing before, just a little different. Okay, step 1, we want to change 0.9999 repeating into a fraction. You should know how to do that. The shortcut method would be what? 9 over 9, which we know to be 1, right? So let's see if that's what pops up here. What do you notice? Oops, I didn't want that to show yet. What did we notice? We noticed that 9 over 9, that's how we would show a repeating decimal, is really just 1, right? So the best type of number would be a whole number, right? So let's pop down and see what it says here now. We can look at it. The best type of number to describe 0.99999 is a whole number. Why? Because this number can be changed into exactly 1. Okay. Irrational numbers can never be precisely represented in decimal form. Why is that? Why can irrational numbers never be precisely represented as a decimal? Why can't we? Like irrational numbers such as pi, such as there's E, weird E, or square root of 2, or square root of any imperfect number like square root of 8. Today we had square root of 10. All of those, right? Why can't we precisely represent them? Well, for the square rooted ones, we can't find a number that will exactly multiply together by itself to give us 2, or to give us 8, or to give us 10. In decimal form, irrational numbers never terminate and they never repeat. No matter how many decimal places you include, the number will never be precisely accurate. There are always more digits that could be written forever and ever. So that is why irrational numbers are not precise in decimal form. Okay, I'll come back here. There we are. And your homework is going to be doing page 18, numbers 1 through 10, and page 19, numbers 14 to 19. I want to just check that for a minute because I want to make sure that I changed that from the yesterday's lesson. I want to just check page 19. I'll come back to you in a second here. I can get it to pause. Something in the way at the top of the screen there. All right. Okay, I was correct. That was not changed. That was yesterday's lesson. I'm going to cross that off. I'm going to cross this off. Just look on Google Classroom. It will be right on Google Classroom. The real thing I wanted you to do for lesson 1.2b is page 18, but only problems number, and I wrote it down here, numbers 11 and 12. I'll have to change this on the slide. 11 through 12, and I wanted you to do page 19. Let's put that here. Numbers 20, 21, 22, 23, 24, 25. So numbers 20 through 25. So this is the correct homework. Let me just circle that. That's what you're to do, okay? I'll put that on Google Classroom so you shouldn't be confused. However, I made a mistake and did not change that slide from yesterday. So have a good day. I will stop my share. Make sure you get that assignment written down. And I will see you in the next lesson. Have a good day. Bye.